Hello, sixth graders. It's been a while since I made a video because we've had our project that we've been working on. I have to say I am super impressed with a lot of the PSAs that you guys sent in. You guys are so creative, you're so smart, and you guys have a lot going for you, even in this time where you could slack off. Some of you really rose to the occasion and turned in some really good projects, so thank you. It was great to see how you took Newton's first law of everything, its motion will stay in motion unless an unbalanced force like a push or a pull acts on them, or everything will stay at rest unless inertia is overcome with a push or a pull. And using that in relationship to wearing helmets and wearing your seatbelts. Some of you guys put together some really funny videos and some PowerPoints, so good job. And that was a great test grade for most of you guys. We're going to be moving into Newton's second law, but before we do that, I want to give you a pretty cool, fantastic fact in regards to gravity and friction. Most things get balanced out in nature. Different forces will work together so that one thing doesn't overcome another thing too much, where things will balance. So let's look at how rain can be balanced out. So we've talked about a couple of things that go against, that are examples of inertia. We talked about gravity and we talked about friction. So how do those two work together when it comes to something as natural as rain? Well, we have air resistance, which is an example of a helpful friction. Remember we talked about how there were some frictions that would hinder and some that are helpful. Air resistance is one that is super helpful. If raindrops met no resistance, they would be falling faster than the speed of sound by the time they reach the earth. Now imagine water flying towards your head faster than the speed of sound. That's a Mach 1, Mach 2 type of speed. Rain showers would be very painful. They would poke holes in roofs, and it would be super painful, super destructive. Gravity's pulling the drops earthward, and air resistance limits their maximum speed, and those two forces are actually working against each other to balance each other out, and soon the raindrops will fall at a constant speed that doesn't hurt. In fact, raindrops get their shape because of that, because of the air resistance pushing against them. You guys remember when I showed you the video of if we drop bricks and feathers at the same time in a normal room, which one would hit the ground first? Obviously, the bricks would. But if we were sealed inside of an airtight room, and we removed all the air resistance out of that room, and we dropped the bricks and the feathers at the same time, which one would hit the ground first? Right, they would both hit the ground at the same time, because if there's no air resistance that's pushing against what's falling down, then which is a type of friction, then there is no friction and it falls to the ground without any resistance. Now, we're going to start talking about Newton's second law of motion, and with this law of motion, I want to give you a little story, okay? And if I could reenact it, I would, but I can't. My dog got loose the other day, and my daughter, and when she gets loose, I don't know about you, if you guys have any pets any dogs that do this, but she just starts running laps like crazy. She goes crazy. She just starts running. And she ran around the house this way, and my daughter ran around the house this way. And they're both sprinting in opposite directions. And by the time they got to the back corner of my house, I come around the corner just in time to see my daughter and the dog come to the corner at the same time, and they collide. And my dog goes flying, and Sophia goes flying, feet out from under her, broke my dog's collar right off her neck. They were both fine, but there were two masses that were moving at a very quick acceleration that met. Okay, now they both weigh the same amount, so they were equal masses. What we're going to be learning about today is how we have a law that says mass times acceleration will equal force. So we're going to learn how those principles kind of go hand in hand with Newton's second law. So let's look at Newton's second law. Newton's second law, most of us will recognize that if we move a 110-pound box, that would be easier than moving a box that's 1,000 pounds or half a ton, right? We can all agree with that, that if I had two boxes set in front of you and I said, all right, you need to choose whether or not you are going to move a box that is 100 pounds, or you can try and move the box that's 1,000 pounds. Some of you may be like, well, I'm going to try the 1,000 pounds, but you're not going to be able to move it. Most of you would choose the 100-pound box because it's easier. Now, Newton's second law of motion states that force is equal to an object's mass and the acceleration of that object. Okay, in other words, if there is an increase in force, that it's related to an increase in mass and acceleration. Meaning, if I put this in simpler terms, it's going to require more force to lift up a heavier box, correct? I would have to increase my acceleration because the mass is increased, therefore I need more force than if I had like a little tiny box that didn't need as much acceleration or much force because the mass is a lot smaller. Does that make sense? That's pretty much what this is talking about. So let's look at the next one. So this is the formula that we would use to illustrate the second law. It's m times a equals f. Well, that's mass, what is in an object, times acceleration, how fast it's moving, equals force. So which one would require more force? Would it be the person pulling a jumbo jet or the person pulling a Jeep Wrangler? Well, obviously this person right here does not need as much force as this person right here. Why? That's right, because the mass of this plane is significantly bigger than the mass of the Wrangler here. So the mass times the acceleration, that's how fast they're having to get it to move, will equal how much force is needed to pull it. So there's several principles that results from this formula. We're going to look at three of them, okay? First, the greater the mass of the object, the greater the force needed to move it. That makes sense, right? The bigger it is, the more force you're going to need to actually get it to move. So, a little bit of force can move an empty cardboard box, but moving a cardboard box filled with a person requires much more force. So if I had a box that was sitting there empty, you're not going to need much force to move it. But if I have a box that has like a sibling or a parent or a child sitting in it, it's obviously going to require more force than if I had an empty box. Same thing, moving a golf ball with a golf club is pretty simple. For those of you that are my golfers, Giuseppe, I go to swing that golf club to hit a golf ball, no problem. I can send it several hundred yards. Well, maybe not me, I have a good slice. But for those of you that are good golfers, you can send it straight down the fairway going a couple hundred yards. But if I'm trying to move a bowling ball with a golf club, that would be quite difficult. The golf ball does not have as much mass as the bowling ball does. So if I'm using a golf club, I'm going to bust it over the bowling ball and not get it to move very much, whereas if I hit a golf ball, no problem. So that's the first principle. Second principle, the greater the force exerted, so the greater the force used on the object, the greater that the acceleration will be. So athletes use this principle quite a bit. The harder you swing a tennis racket or a baseball bat, for all my baseball players and my tennis players out there, or softball players, the harder this person you know who this person is for all my baseball fans out there? This was back in the 1990s. Yeah, Ken Griffey Jr. The harder you swing a bat or a racket, the faster the ball accelerates after you hit it. So think about this. I go to swing a bat and I seriously swing it like this. Not swinging it very hard. And I hit the ball, but that ball's just going to kind of go forward maybe 15, 20 feet, rolling, and then come to a stop. But if I'm lining that ball up and I'm swinging it as hard as I can and I connect with that ball really well, I'm going to send that ball a lot farther. Why? Because the acceleration in my swing was a lot harder with a full swing than it was when I just kind of like had this dinky little swing. Okay, so the greater the force exerted, the more force I put behind swinging, the greater the acceleration will be of what is being hit. Okay? Third principle, the greater the acceleration, the greater the force exerted on an object. This is why it would take more force to throw a fast baseball pitch than to throw a slow baseball pitch. That fastball has more acceleration, so it requires more force. So if I'm going to throw a baseball, the greater the acceleration of my arm, how fast I bring my arm forward will determine the force behind the ball that's being thrown. So if I'm sitting there and I'm just like, just this little dinky throw again, it's not going to go very far. My acceleration of my arm is slow in comparison to a fast throw. So, why does it take more force to pick up a full water jug, like a gallon-sized jug, than it takes to pick up an empty jug? Here's the question that you need to answer for today's lesson. You are going to email me your answer. Email me your answer, okay? Why does it take more force to pick up a full water jug than it takes to pick up an empty water jug, like a gallon container? I want you to identify the principle that supports your effort. There were 3 principles that we talked about. Remember, the first one was the greater the mass of an object, the greater the force needed. So the bigger the object, the more force it needs to actually move it. The second one is the greater the force exerted or put on an object, the greater the acceleration it will be. And the third one is the greater the acceleration, how hard I'm throwing, how fast my arm is moving, how fast my leg is kicking, the greater the force exerted on an object. You need to tell me why it takes more force to pick up a full water jug than an empty one, and then give me the principle that supports your answer. Again, please email me that answer. I don't want you posting it. Your emailed answer will be your daily grade as well as your attendance, so make sure you get that to me. Tomorrow, we'll talk about an arm wrestling competition and how this relates to Newton's law. And let's see if I can actually get out of this. All right, bye guys, love you.